In the last learning sequence, we talked extensively about the force that a magnetic field applies to a moving charge. And we talked a little bit about how magnetic fields are also made by moving charge. We had a little bit of current in a wire, that's a moving charge. We had a field going around the wire. If we had current in a loop, you made a field inside. We talked about natural magnets. They're actually little atomic currents flying, going around the atoms. But now what we're going to do in this learning sequence is talk about making a magnetic field in more detail with math. Okay? So you do that with a law called Biot Savart. And they were both French, so the T's are silent. If I had to define the Biot Savart law, I would say that it is the B field due to a current. Also, I'm going to just say current all the time. And that's just going to mean a wire carrying a current. Okay, so the wire is implied. Really, we're just speaking generally about really any current. Okay, but I'll draw them like they're wires. So let's imagine then we have some wire here. Doesn't have to be straight. Right now we're doing just the general Biot Savart law for any current. Like that. There's a wire. It's got a current I flowing into it. Okay? And you want to know what's the magnetic field somewhere like here at point P. What magnetic field do these moving charges create? Okay. You're not asking much. That's all you want to know. So what is B at P? And you'd think we'd have some simple formula like Coulomb's law. But we don't, because there are no point currents. Right? When we're doing electric fields, point charges can add up and give you this nice simple expression. When we went to continuous charges, we had to do an integral. We had to have a differential. Well, with a magnetic field, we have to go straight to the differential because there's no point currents. Any current you have has to be some distributed current. It has to be flowing through a wire. You can't have one place where there's a current because where did the charge come from and where did it go? So here, we have to go straight to a differential definition. So let's do that. So Biot Savart would say then that you have to think about a little piece of the wire. You have to divide it up into little imaginary differential elements. So remember these things. Differential elements are just imaginary little chunks. And when we're thinking about these little things, then you can treat it like a point current. So one might be sitting here, and we give them a little vector differential ds. That just means the path. That's really the length in that case along the direction of the wire ds. And we want to know what differential magnetic field dB is created by this little differential element ds, and then we add them up for the whole wire. Okay. So the answer is dB at point P is mu naught over 4 pi. So it's a new constant. We'll define it in a minute. Times the current, I, it's a big I, times ds crossed with r, hat. Oh my gosh, over r squared. So that looks horrible. It's got everything that you don't like in it. It's got a cross product inside of an integral with a vector differential and then just a unit vector just to make it extra horrible. Okay? But let's go through and figure out what they are one at a time. So ds, we already talked about. We would call that the a differential element of the wire. Differential element of the wire, and its direction is, of course, along the wire. That's usually how you set up a differential element. R, let's look at R. R is the distance from the ds to the point P. And you'll see it written this way in books a lot with just an R. But if we really want to understand the whole setup, it's actually better to make it a vector and say it's the magnitude of that vector. It's the more formal way to say that it's the distance. That way we can define the vector here. Okay? If we do it that way, I can show you R. R is just the vector from ds to P. R is just the separation. So it's the vector ds to P. And now this makes r hat easier to identify and to draw. We know r hat would then just be the unit vector along that direction. So if I had to draw r hat, assuming unit was only that far, there's r hat right there. R hat, unit vector along r. And let's see, 4 is the fourth integer, and pi, you know what pi is, and mu naught, that's the one that is left. Mu naught is the permeability of free space. It's a lot like epsilon naught for the electric field, the permittivity of free space. How much electric field do you get for some charge? Permeability of free space helps you figure out how much magnetic field you get for some current. It's equal to 4 pi times 10 to the 7th. It must be Tesla meters per amp. That's the constant you want to use. 4 pi times 10 to the 7th Tesla meters per amp. So now what we're going to do is keep going and think about how to do this integral. Let's use the Biot Savart law to get the B field, the B of a long, straight wire. I'm sorry, a long straight current. We're always going to use the word current rather than wire. So a wire doesn't have to carry a current, but a current has to flow in a wire, we could say. So, Biot Savart. So let's draw it first. There's a wire. Looks suspiciously like just two lines, but it is a wire with current flowing down it like that. And we want to find the B field at some point P, a distance, at a specific distance from the wire, say A. So if we go to here, there's A. Okay, so we apply the Biot Savart law. Let's go ahead and just write that differential from the Biot Savart law. dB, the little differential field element that's created by a little ds, is really what Biot Savart tells us in this case. That's the little dB. And you can imagine we're going to sum it up. Okay. All right, so dB is mu naught over 4 pi times I times ds crossed with r hat over r squared. Okay. So now we got to deal with ds cross r hat. Okay. What in the heck is that? Well, let's see. So here's the vector ds. The vector r hat, remember we think of a vector r from the ds to the point P. So there's r. So therefore that is r hat. Okay. So if you want that cross product, you just, well, you say ds cross r hat is the magnitude of one, ds, times the magnitude of the other, which is just 1, times the sine of the angle between them. Well, the angle between ds and r hat is just going to be this angle of this right triangle. And you can see that'll be true anywhere we put ds along the wire. It's always going to make a right triangle. That angle will always be theta, so sine of theta. Okay, if we plug that in, then we get dB is mu naught I over 4 pi. And then, I want to write it the same way, we have ds sine theta over r squared. And now we need a direction. Okay, this is a vector, and this clearly is a vector with some direction. It's a cross product. Now this is a vector, but this is really just the magnitude of ds cross r. We don't have the vector part. Okay, so to do this problem, you almost always want to set up a coordinate system. So let's set up a coordinate system. There's the x direction, we'll say, is along the wire, along ds. There's the y, and x cross y is out, so this z must be out of the board. Okay? So our ds cross r sticks out of the board. So there must be a k hat on here. and therefore there must also be a k hat on there. So that is our dB, and it's a vector like it should be. So now we want to integrate along the wire. The reason you set up a differential element is you're going to add them all up on whatever physical object you're working with. So here ds is aligned with the x-axis. So the little ds's basically become dx's. So we can pretty much just write it like that. We could say that dB is mu naught I over 4 pi times dx times the sine of theta. But remember also, if you're going to do this integral, you got to get everything that varies in terms of x. You can't have something that's changing, like theta or r, written in terms of theta and r. If you're going to integrate with respect to dx, you got to write everything with respect to dx. These were just constants. They got to stay how they are. So let's look at sine theta and say, what is it? Well, let's see. Sine of theta is opposite over hypotenuse. So the sine of theta is a over, funny looking a over this hypotenuse. This hypotenuse is the square root of x squared plus a squared, right? Pythagorean theorem. So that would put the square root of a squared plus x squared, like that. So there's dx times sine theta. You got to be a little bit careful. Actually, this is going to a negative x value. So technically, on some problems, it's important that you put negative x in here, but it's going to get squared, so negative doesn't matter. And just to save room, I don't want to write negative x squared. Let's see. So that takes care of those two. And then we have an r squared in the bottom here. R, remember, is really just the magnitude of the r vector. It's really this distance here to here. Well, we just did the Pythagorean theorem, but we can do it again. 1 over the square root of a squared plus x squared, but then it's squared, like that. So you have an a squared plus x squared. Okay? And it's in the k hat direction. So there's your integral. And you can see quickly one thing you can do is combine these two. It's really the integral of mu naught I a over 4 pi dx over a squared plus x squared to the 3/2 once we put it together. So next board, we'll go through and finish the integral. All right, let's finish up our integral here. So we had said that the V field, we're going to integrate these dBs. So what did we have? We had mu naught I over 4 pi, and we had an a that can go with the constants, here, like that. And we had dx over x squared plus a squared to the 3/2. We got all this by combining the sine theta and the 1 over r squared. And the last thing we need are limits. On the integral, we're describing a physical system. This isn't calculus where the limits are meaningless. This is a real system. So we have to have real limits. In this case, we're doing a really long wire, so we're going to put it from minus infinity to infinity. This same integral could be used to find a finite wire. If you put this at the origin and just made it from minus L over 2 to L over 2, you could plug those in and get the answer just fine. But let's do the infinite case. Okay, so B equals, let's keep these constants, mu naught I a over 4 pi. And then how to do that integral? Now, it's not an easy one. That's one of those that you look up in a table, or you put in your computer, or you go through and integrate it by parts or some horrible thing like that. But that integral, in the end, you get x over a squared times x squared plus a squared to the 1/2, to the minus 1/2 if you put it in the top, over that to the 1/2. And then you evaluate that from minus infinity to infinity. Now, if you don't believe me, you can take the derivative of this, and you'll get that. I promise I've done it. It's a lot of fun, but it does work. A bunch of terms cancel, and it works. So now we have to plug in our limits to get B. Let's see. So B, mu naught I, and we can see one of those a's goes away. Basically, this a is now in the bottom over 4 pi a. Yeah, 4 pi, this a stays, and that one gets canceled with that one. And we're going to plug in, we're just going to keep this on the outside and plug in infinity and minus infinity. Now, plugging in infinity and minus infinity. Plugging in infinity. So what we're going to do is just plug it in and think about what do we think we should get. Okay? If you have infinity over the square root of infinity squared, which doesn't seem like it should be a real thing, plus a squared, what do you get? Well, if you do infinity, things are going to go wrong. So let's just say big. Let's do big and little. Okay? Infinity is really big. Compared to a, this measly little separation, it's big, and a is small. So let's just think, what if we plugged in big over the square root, and I'll just write it the same way, big squared, which is really big, plus what? Small squared to the 1/2. What would that be? Okay? Basically, in physics and math, this comes up all the time. You have something big plus something small. And if the thing that's big is a lot bigger than the thing that's small, you just ignore the thing that's small. Who cares? Okay? And in the limit that something's actually infinity, then it's actually perfectly true. Right? Often we do this for an approximation, but here it's really true. If we just ignore the small because the big is so big, then the square root of big squared is just big, and big over big is 1. Right? So there, that's how you plug in infinity. This is fast and loose. It can get you in trouble, but it's good enough for right now. So we plug in 1, and now minus what? Now we're going to plug in minus infinity. We've got to do this limit. And you might think it's going to give us 1 minus 1, but it won't. Let's see what's actually going to happen. If we plug in minus infinity, it's minus big. And this would actually be minus big squared plus small. Okay? So if you do that, again, this is minus big squared. It's something really big. And this is small, so the small goes away. And then this remains positive, but this one was negative. Okay? So you have minus big over big. Oh, that's minus 1. So it's 1 minus minus 1, which of course is 1 plus 1. So let me get this out of the way. And let's see, then you get a b, in the k-hat direction. You get b is, this is going to be a 2, and it's going to knock that 4 down to a 2. Is mu naught I over 2 pi a in the k-hat direction. So that's telling us once we add up all these dB B fields, that's the B field we're going to get. And now I've seen something that's a little bit ugly here is this vector I drew in the wrong direction because I was thinking of an electric field. I don't want to reshoot this whole thing. So what I'm going to say is that's an Easter egg for you to notice during the whole lecture. Of course, dB is like that. So that's a little dB. Now we've added up all the dBs, and we have the total B field. And when I circle it, I'm going to leave room to write something here because there is one thing we got to think about. That's the direction of the B field in this plane. In the plane of the board. That can't be the B field everywhere. If I just write the B field everywhere you go is in the K direction, then it's going to be this thing that varies, and even out here it would be in the K direction. And that's not the case. We know the field does something else. We're going to talk about it in a minute. So we've really only solved for it here. And where we go, well, the reason that has to be is when we figured out this cross product. We crossed ds along the wire with r hat going this way. They were in this plane. That gave us the direction of the B field. If you start coming out into space out of the board, r hat changes. Right? And then the B field direction would change. So we'll talk about that in a minute. But just to be clear, this shows that the B field, it goes down as 1 over the radius. Right? If A got bigger, the B field gets smaller. So you can think of that as we've solved it as a function of radius away. But it's only in the direction, it's only in the plane of the board. So now in a second here, we'll draw it and see what it looks like. So we calculated the magnetic field for a wire, but we only calculated it in this plane. And we calculated a B field in the z direction. We know it's actually more complicated than that. So let's think about the B in 3D. Okay. To do it mathematically, we would have to deal with that cross section in 3 dimensions, or that cross product in 3 dimensions, and that would be a pain. Instead, let's just think about the answer we had and think about what it would look like in 3D. So if here's the wire, and here I'm kind of drawing it with some perspective going off into the sunset. We imagine this little ds here, this little differential piece of the wire. And if we went up to some height a, like that, what we figured out was that, if you're at this ds and you're up there, there's r. So ds cross r was that the B field came out like that. So the B field was like this in that case. So before when we drew it, that was sticking out at you. Now I'm kind of drawing it in perspective. What if we were to go down at the other side? Down here, we could go a distance a down there. Now r has changed its direction. R is now that way. ds cross rb into the board, or in this perspective, I'll draw it kind of like that. All right, so we have it coming out this way and going in that way. What if we came out to the side, come out like this? Oops, let me draw it kind of like a distance a like that. Now r is going this way out, ds cross r, it'd be down, right? There's b. And if we went back this way, distance a, there's r. ds cross r, it'd be up. So you can see what's going to happen is it goes around, which is exactly what we calculated last time, or what we mentioned in the last learning sequence. If we have a wire and the current is going this way, we know, we just calculated, you get a big B field here coming out and going in right near the surface of the wire. But now, with our new formula, we know that it gets weaker. It goes as 1 over r, mu naught I over 2 pi a. Really, the a is the radius, so it's really mu naught I over 2 pi r. So as you get farther away, the magnitude will get smaller, which I'll just represent with slightly smaller looking vectors. And then here, oops, it's going to get smaller like that. And then really small. Okay. So that's if you wanted to look at it in the plane again. We can think about the fact that it goes around the wire and that its magnitude goes down as you go away from the wire. In the previous learning sequence, we kind of drew it like this. We just drew single field lines going around the wire, like that. And also remember that there's a right-hand rule involved. Before we told you that the way to get the direction of the field going around is put your thumb along the wire and your fingers curl around with the direction of the field. Well, we showed that's true today with our actual calculation of the direction of the magnetic field around the wire. If you put your thumb along ds along the current, you'll find your B field, your fingers curve around with the B field. So it all makes sense. We only calculate it in one plane in 2D, but it actually matches perfectly with what we said before about the B field in 3D going around a wire.